So previously we did the concept of the electric potential, okay, and the graph due to um, any one any one source charge, okay, and now we have to do the graph for the two charges, right? So we also did the graph for the two charges and the variation of the electric field, okay. So be careful. This is not the variation of the electric field. This is rather the variation of the electric potential graph, right? So first thing that you should remember is that the electric potential is a scalar quantity and it will always be added at every point, okay. So the electric potential due to the negative charge will always negative, okay, and the electric potential will for from the electric potential of the positive charge will always be positive, right? So sorry. Mm, Potential will be negative, okay, for this charge, and um potential will be positive for this one. Okay. So the resultant potential is going to be the summation of the two potential. Okay. Um, if you say that this is V2, and this is V1, okay, so the summation of the potential will be the net potential will going to be the V1 plus V2, right? Now, okay, so this is something that I've wrote, okay, and yep, the net potential is going to be the potential between the potential. Okay, let me just write down the equation. Okay, so the net potential V net is going to be V1 plus V2, right? Where V2 will ultimately become negative due to the charge, right? But you don't have to put the negative sign because the negative sign by default shows a direction change, okay? So or the change in the electric potential, but we are not finding the change in the electric potential. We are rather finding the resultant potential, okay? So if we try to make the graph, okay, so we know that the electric potential inside the sphere will always be positive, okay, so this is positive, okay, and the potential decreases inversely, okay, outside the sphere, okay, so it decreases inversely, and this is the resultant graph, by the way, okay, it's not a specific one for the specific value, okay, and the potential increases in the opposite direction, okay, and it will be constant inside, right? And the net potential will be zero at this point. The net electric field will be non-zero, right? Because since it is a positive negative charge and the field line, you can see that the field line is continued, right? So the field cannot be zero, right? So if the field line does continue, then the field strength will be zero, right? So now, mm, okay. So at this point, by the way, at the center point, the object will be moving with a maximum velocity, right? So you should remember that. Uh, Test charge move with constant velocity, constant and maximum velocity, or just maximum velocity. Okay, so if they ask you to find the point of the maximum velocity, then you have to work out at that point. Okay, and okay, fine. So if we try to find out the potential at this point, okay, at the point where we have the net potential zero, we're basically finding the ratio because this type of question is like very common in the exam. So come on. Okay. So the net potential at any point is given by V1 plus V2, right? The potential, the sum of the potential of the two charges, right? And at null point, the net potential is zero, right? You can see in the graph, right? And the individual potential will be V1 is equals to K, and then we have Q with a positive sign divided by, let me take the distance as, by the way, the distance from this to that point is going to be D minus X, okay? So it is D minus X. You don't have to put the negative square, right? Because it is like, it does not require any square, right? If we do for the electric field, then we have to square it, right? For V2, it is going to be negative KQ over R over X in this case. Okay. Now, because that distance is X, okay, from the charge to the source charge. Okay. And now if we if we put that in the equation, so it looks like this: KQ over D minus X, and then plus, and then KQ with a negative sign over X, okay. At this time, this q is going to be this q is going to be negative, right? Now, if we solve, so it become k. Okay, I'm just putting 1 and 2 here, okay, to differentiate the charges, right? Over d minus x is equals to kq2 over x, right? So k and k goes off, and the ratio of the charges is going to be this one, okay? So d minus x divided by x. Okay, is that clear? Oh,
Yes, sir.
fine. Perfect. Okay, so this is a concept, right? Now, another concept is, okay, another concept is if I have the two like charges, right? So you can see that their electric field is zero in between, okay? By the way, let me just the charge value will, okay, the acceleration decreases, minimum velocity. It should be minimum velocity, not maximum velocity. Okay, the maximum velocity will be in that case. Okay, so for this one, if we try to make the graph, okay, so okay, and this is in joules per coulomb, and this is the distance in meter. Okay, now let's say, okay, let me just make it in the negative because these are the two negative charges. Okay, so this is the surface of one charge. Okay, and this is the surface of the other charge. Okay. Okay. If the two charge values are same, the magnitude of the two charges are same, then the the minimum point will be in between the two, in between, like exactly in the center, right? So let's just make this thing. Okay. Okay, inside the sphere, the electric field remain constant, right? Electric potential remain constant, and outside it will be zero. It will be inversely proportional, not zero. And constant and minimum outside. Okay, fine. So this is a concept, and this is the minimum potential that you can ever get. Okay, so this is the minimum potential that I am having. Okay, perfect. Now, oh, okay, so at this point, the electric field will be zero. Okay, minimum potential. Okay, at this point. Okay, and zero electric field. Okay, zero electric field, right? And at that point, if we try to find out, the object will move with a maximum velocity. Okay, zero electric field, zero force and acceleration. Okay, and maximum velocity. Okay, so the object will be moving with the maximum velocity at that point, and then its velocity decreases as it move on. Okay, is that clear? Now, always keep in mind the actually I told you this point that the gradient of the potential graph is going to be the electric field. Okay, okay. So always keep in mind um, the gradient of potential is electric field. Okay. Now the gradient varies. Okay, it is zero at the maximum point at this point. Okay, and then increases in the opposite direction, right? So as the field and force and acceleration, right? So always keep in mind, right? The field, force, and acceleration are connected directly. Okay, while the gradient is related, while the potential is related with the field through the gradient. Okay, so field, force, and acceleration are related directly. Okay, are related directly, right? So now, so the minimum potential at any point is given by the summation of the potential difference at due to the two charge, right? So this is something that you need to remember, okay? And they can ask you to do, okay, so okay, so you should know that the net potential should be V1 plus V2, okay? And then you can do that KQ over R. Okay. And then plus KQ2, this is 1 over X. Okay. Right. If we consider that the whole distance between the two is D. Okay. This is D. And this is, let's say, X. Copy and paste. Okay. And I should have the charge as well. Okay. Let me just erase. Okay. And over here. Okay. So if this is the scenario, then this is going to be the equation. Okay. By the way, please keep in mind the potential at the surface is actually depending upon the charge value. Okay, so if you have the greater charge, then this value will be larger. If you have the smaller charge, then this value will be smaller, right? And the minimum point will be further from that charge. Okay, so these are the 2 points that you should remember. Okay, the first thing is surface potential depends upon the charge stored, right? And second thing is uh, minimum point minimum point can shift can shift from can shift okay sorry can shift rightward, okay, if charge to the left would be greater. Okay, so these are something that you have to remember. Okay. Now let's talk about okay, let's talk about this is the concept. These are all the graph that we have. Okay, now if we talk about the work done on the test charge, okay, we have to discuss some of the concepts and then the chapter will be done. Okay, so if we have, let's say, a charge, okay, fine, and okay, and I have another charge right here. Okay, the separation between the two charges is, let's say, um, 12 micrometer. Okay, and the charge move from charges at point A. Okay, let's say this is point A. It moved from point A to point B in this direction. Okay, and point B is, let's say, 7 meter from this distance is 7 micrometer. Okay. Mm, 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 mm. So by the way, if we consider this as just millimeter and this as 4.8, this has a value of 4.8, um, um, 4.8 microcoulomb in nanocoulomb. And this is the elementary charge, okay? Elementary charge. It has a value of 1.6 exponent negative 19 with a positive, right? Now, and this is point B, by the way. So the charge is moved from point A to point B. Obviously, you have to apply force in order to move the smaller charge to point B because both the charges are of the same type. Okay, so the smaller charge will not move to the bigger charge easily because they repel each other, right? So when you apply the external force, we have to find out the work done. Work done in order or work done to move from A to B, right? So work done from A to B. Right. Now, so work done is basically mm, wait, this is the formula. Uh, so the work done has a formula of work done is basically electric potential energy. By the way, please keep in mind you're not allowed to use this formula. Okay. W is equals to work done is equals to F times S. Okay, this formula is not allowed. Okay, because the force is not constant. Okay, so this formula is not allowed in non-uniform field. Uniform field. Okay, as the force is not constant. While you can use this, while you can use this in uniform circular motion, in uniform electric field motion. Okay, so but over here there isn't the uniform motion. It is basically the non-uniform electric field. So in the non-uniform electric field, the force won't be constant, and that's why we are not allowed to use this formula. Okay, so the basic formula for the electric potential energy is KQ over R, right? This is the energy formula, right? And since we are finding the change in energy, right? So R should be the change, right? R should change from A to B, right? So if you put in the values, so you will get 8.99 exponent 9. I'm taking KQQ common because this thing remains the same. Okay. And let's say I have the other Q is 4.8 nanocoulomb into negative 90. Okay. And divided by the value of the R from B to from B to the charge value. So it is 7 exponent negative 9. Okay. And we have to do final minus initial. That's what I'm doing. Okay. Now this is for the charge value of this is kq cube. Okay. And if I take this thing common, the denominator, so I can write this as 1 over this minus 1 over the other value, right? Which is 1.6 exponent negative 19, right? So if you can calculate, you'll get work done how much, bro? Right? Yes. How
1
much?
minute.
Sorry?
एक सेकंड से कैलकुलेट कर रहा हूँ.
Okay. Yes, how much? It should be somewhere around 4.096. It is exponent 9, by the way. Exponent 9 into this is 4.8 exponent negative 9 is nanocoulomb into 1.6 exponent negative 19. Okay. And then I have 1 over 7. Okay. I just input this value incorrect. 12. This should be millimeter as well. Yes. It would be negative 3. Okay. And negative 3. This one as well. Right. So,
4.11 आ रहा है सर.
okay. So you're saying 4.11. Any experiment, bro?
Oh,
No,
हाँ,
no.
sorry. Minus 10 to the power of minus 16.
Minus 16. Good. Okay. So this is the work done in joules. Okay. But if you have two charges, so the potential difference due to the two charges cannot be found that way, right? But I'll explain that two charges concept in the paper, like in the question tomorrow. Okay. So I'm stopping the class right here. Okay, the chapter is done. Okay, now we'll do some of the question tomorrow, inshallah. Say, चल चलो जी.
Uh,
Okay, take care. Hafiz.